In this video, we'll be looking at real and complex roots and using them to be able to write a quadratic equation quickly based upon those values. To start, we'll look at three quadratic equations and find the roots of them because that's something we've practiced many times before. And if you use your graphing calculator to find those roots, what you'll find is that all three of these quadratic equations have complex roots, and since it is a second-degree polynomial, you'll have two roots that are both complex numbers. Now, as you take a look at these complex numbers, you should notice a pattern that exists within each of the problems, and they are very similar to each other, the same first term, but the opposite second term. This is a plus 3 versus negative, positive I versus negative, positive 4i versus negative 4i. We call those conjugates, where it's got the same first term and the opposite second term. If you have a quadratic equation that has a complex root, there will always be two complex roots, and there'll be complex conjugate pairs. So what we'll do now is we're going to do some operations with those conjugates that we just found. So we're going to find the sum and the product of each. Now the sum for each of these should actually be pretty easy because when you add up your two values, all you need to do is take your 1 plus 3i and add it to 1 minus 3i, and for each of these, what you'll notice is a similar thing occurs where the 3i's just simply cancel out. So the sum is going to be equal to 2 for the first example, and the sum for the second example is going to be equal to a negative 4 because again, your I and your negative I will just cancel, and the sum for the third example is going to be equal to 6 because the 4i and the negative 4i cancel. Now to find the product, what we're going to need to do is we're going to do a little bit more work where we need to use our generic rectangle to help us organize our work. So to start off, we can put our 1 plus 3i across the bottom, and we can put our 1 minus 3i on the side. And now we just fill in our products, so we multiply each of these spots. This is a 1 in that box, a 3i here, a negative 3i, and then finally a negative 9i squared. So I took my time with this one here because that's where most of the mistakes by students are made. Because as we take a look at that, if we were to try to simplify this, we take a look at negative 9i squared, and we know that I squared is equal to negative 1. Right, so that's a really important part for us to remember for our work, because really if we have negative 9 times I squared, which is negative 1, that's negative 9 times negative 1, so that cancels out to be equal to a positive 9. So now we have a little more, we can simplify because you notice that you have a negative 3i and a positive 3i, and those are actually going to cancel out. So those will cancel, and so what you're left with is simply a 1 and a 9. That you're supposed to add all those together, so the product of all this is equal to 10. And that's really impressive because what you can take is a complex number, multiply by another complex number, and you're going to end up with a real number with no complex parts. And so that will always be the case with the conjugate, as you'll see in these three examples as we do our multiplication. So let's keep on going here. So for the second example, we have negative 2 and a positive I on the bottom, negative 2 and a minus I on the side. As you multiply each part, this is a positive 4, a negative 2i, negative 2 times a negative I is now a positive 2i, and then you have just a negative I squared. And again, your I squared is equal to a negative 1, so this all cancels out with a negative and a negative 1 equal to a positive 1. Right, so catch that again. You have a negative here already. I squared is negative 1, so negative times a negative is a positive. And we notice again that our 2i and negative 2i will cancel each other out, so what you're left is with a 4 plus 1, and so that the product is equal to 5. We'll go through this final example a touch quicker. So as you multiply 3 plus 4i times 3 minus 4i, when you multiply all those things on the inside, what you end up with is a 9 on the bottom left, 12i, a negative 12i, and negative 16i squared. Again, I squared is equal to a negative 1, so this whole thing cancels out to be a positive 16. Negative 12i and a positive 12i will cancel. So what you end up with is 9 plus 16, so the product is equal to 25. So not only are the actual operations of finding the sum and finding the product important on its own, but what you notice is that if you have conjugates, the sum will be a real number with no complex part, and the product will be a real number with no complex part. And that's true for only conjugates when you're doing that work with each other. So that's important to remember. So remember, our goal was to be able to take the root or given roots and be able to write the equation. And so we've been able to do that if we started with factored form. And so we started this unit by giving you some real roots like -5 and 3, where you turn them into the factored form, and then you wrote it in standard form just by your simple multiplication. So we have these two examples. What we just did now is we looked at some complex roots, and we noticed how they're always in a complex conjugate pair, and our goal now is to relate those to those equations as well. It's a little bit more difficult when you have your complex examples to just set it up in factored form, although not impossible. So what I want you to visualize is what are the connections between these roots that we see over here with their equation. It might help if we take a look at little pieces at a time. And so if we look at the constant that exists in all of these examples over here on the right, and now take a look at these examples that we have on the left, or the roots that were given on the left rather, and what you see is that there might be a connection between these numbers that are the roots and those numbers that are the constant. So if -5 times 3 is equal to -15, 10 times -7 is equal to -70. And the three examples that we just did that are here, we have those products listed. So the product of each of your roots is the constant that's on the end of your quadratic equation. So that's a real quick way to find out what the constant is. So we've got the constant figured out. Now our goal is to figure out what this number in front of the x is going to be. And so again, as we take a look at our roots and try to think about what relationship those have with these values, you have -5 and 3 and 2, and then 10 and -7 is going to somehow create a -3. Perhaps it might be better if I write it this way, where I put a negative in front, so we have the opposite of whatever this value is in this location. And now if we look at our -5 and 3, that adds up to be -2. 10 and -7 add up to be 3. Our conjugates that we just practiced and looked at, when you add these up, you get a 2. When you add this second to last example, you get a -4. And the final example, you add those up and you get 6. And you see, that's where your sum is found for all of our examples. So, when given two roots of an equation, a quadratic equation in standard form is going to be as follows. Y equals x squared minus the sum, or opposite of the sum, times the x plus the product. It is important that you're careful, because I have emphasized this already, and this is the number one spot where students make mistakes, and it's due to that factored version. So as we take a look at how that comes here, instead of doing it piece by piece, I put it all up here at once. Our roots were -5 and 3, so x plus 5 and x minus 3 are the factors. When you multiply those with the generic rectangle, it's the opposites that create the factors, right? So x plus 5 and x minus 3 versus the original given roots. So when you multiply those, you have 5x and a -3x, which adds to be a positive 2x, which is the opposite of the sum of your roots, right? Because the quadratic equation comes from the multiplied version of your factored form. You can do that with your complex numbers as well, but it's a heck of a lot more complicated. So going backwards from your zero product property rather, if you start with 3 plus 4i and 3 minus 4i, then your factors are going to be x minus that quantity 3 plus 4i and x minus that quantity 3 minus 4i. So on the bottom, what I actually have is this first factor, because you have to distribute that negative. And over here, you have the second factor because you distribute that negative as well. And so scratch that, it's the other way around, but you get the idea, I hope. So this is the x minus 3 minus 4i across the side. And when you multiply, you get all this stuff inside that generic rectangle. So if we look at trying to simplify this, because this is pretty complicated looking, but stuff does cancel. You have this -4xi and a positive 4xi. You have a 12i and a -12i that are going to cancel. Again, you see you have your I squared, which is -1. So this all turns into a positive 16. So when you add it up, you have just the x squared. -3x and a -3x is a -6x. 9 and 16 is a positive 25. So that would be the way to do it with a generic rectangle. Which I must say, we do not expect you to do your work using these generic rectangles, although it does work mathematically. That's where the proof comes from. This is the shortcut that will always exist. You do y equals x squared, and the opposite of the sum times x plus the product.